in a sorry, in a continuous system or analog system is, let's say we have a signal in terms of time, right? And we can differentiate it, or we can so-called integrate it, okay? And we often operate in terms of the Laplace domain, right? Where it is in terms of you transform a certain Laplace where you transform a certain function in terms of Laplace e minus st dt, right? If you still remember, then you use this thing to transform the Laplace. Alright, so this is in terms of the continuous system. However, when we talk about discrete system, is all the points, and we deal with it in terms of the z, right? If you still remember the a, z, k, something like that, if you still remember. Therefore, this word z, it's somewhat same as s in the Laplace domain, like s plus a, s plus b. And normally Laplace, we write things in terms of function of s. This means that it's Laplace. So therefore, in the digital world, we will talk about in terms of z. And also, we didn't operate in terms of the function of time. We actually translate the function of time into somewhat the function of k, or maybe not ek, but rather than uk also. Alright, so this somewhat uk is somewhat like a function of time, while the Laplace is somewhat the z transform. Okay, so with this concept, let us go to something. So in the Laplace domain is L of s, right? In our z domain, we call this the e of z. Alright, and instead of function of time, we call this the e of k. Alright, L for Laplace, z for z transform, or as the name suggests. Okay, and the transformation will transform that particular ek, this particular ek over here, using this summation z minus k. If you still remember, e is what? E is in fact the input, right? U is what? U is in fact the output. So we are actually summing things out in terms of the inputs itself. So we have a lot of e's. Alright, we sum it up. In fact, we're not summing up the e, but rather than summing up the k. So from minus infinity, alright, to infinity, when you sub in the k over here. Okay, so we're gonna do something of this sort. Alright, and I will believe we'll revisit this derivation again. Alright, because there will be a r naught, small capital R naught and a capital R naught that bound on the magnitude, that allows the function to converge. This means that you converge to a certain value or converge to 0. This means it's stable. Alright, so I think we'll revisit this once again in the future. So I'll just carry on now. Now, just a brief of the application of the transform for our trapezoid integration. The trapezoid integration, if you remember back, it's this equation. Alright, because this has a few lot of variables, so we can actually play with it to transform it to a better one. Alright, and therefore we are still presented in terms of the uk. Alright, this is the current input plus the the old input, alright, equals to your new input, if you should remember. But strictly speaking, now since you already know the current, the old and the new, strictly speaking, the u over here is in fact the output, alright, plus the input, the previous input I would say, equals your new output. Alright, strictly speaking now, since you already know all this stuff, because u is in terms of output, e is in terms of input. Alright, okay, now to the best of my knowledge, this uk minus 1 should be input into here. When it's input into here, interaction with the trapezoid system, with this, you'll get a data at here, which is uk. Alright, so at this point is uk minus 1 plus a certain trapezoid system, I would say, integration I would say. So using this formula, instead of writing this tk minus 1, I write as t over 2, while this one is simply the same as this one. So therefore I have something of this representation. Alright, at least I didn't cheat your feeling in terms of the trapezoid formula. If you still remember back the transformation of ek, this is the transformation where summation of k equals to blah 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 blah. Alright, it's exactly the same as the one I've shown you earlier, although it's a bit disfigured. Okay, this is ek, alright, and then this is z minus k, something like that. Alright, so simply when I apply this z transformation, this uk will be transformed over here. So you're just simply subbing in, instead of ek, you sub in your uk. Alright, instead of uk minus 1, you sub in as uk minus 1 with all this stuff, extra stuff. Alright, so I'm just simply subbing in all this with the summation stuff. Alright, ek minus 1 is also here, as you can see. The rest are just the operation of the z transform. Okay, now for this one, this case, I should have drawn this one. For this case over here, we can, because it's k minus 1, right? So if it's k minus 1, we can simply, alright, state that j is equals to k minus 1. What I'm doing right now is to transform this one, or not transform, but rather than rearrange this one into this one. Okay? And you may ask me, where the hell does all this go? I don't know yet. Later we see how. Okay? Now let's continue first. So I'm going to transform this into this. And therefore, what I can do is to sub j is equals to k minus 1. So if I were to do that, alright. Oh, okay. So this thing is being over here. Alright, meaning now this is being placed over here. Since j is equals to k minus 1 in this case, therefore I sub my k minus 1 as j. I sub my minus k as minus j plus 1. Alright, so I'm simply rearranging. For example, if I want to put in terms of minus k, so I'll just bring k to this side, I bring j to this side. What I have is minus k is equals to minus j minus 1. And therefore if I factorize, I will have minus j plus 1 is over here. Alright, now actually missing one step. Alright, missing one step, meaning this one over here, I can actually change it to z minus j, z minus 1. Alright, so I'm actually re-representing this one as this one, because it's simply z minus j. Okay, for example, z minus j minus 1 is equals to z minus j, z minus 1. Alright, it's just multiplications type of thing only. Alright, so when I do that, what I will have is this one. So I can definitely cancel this one. Okay, then I bring this, I factorize it out as z minus 1 over here. So I cancel out this one also. So what I have is uj z minus j. Alright, so if you bracket this one, do you find this very familiar? This is in fact the z transform of uj. Alright, as you can see, e and z minus k. Now it's the summation of j and z minus j. And also, I also almost forgot, is that when you sub k as minus 1 is equals to j, then you have to also change from k to minus infinity to j to minus infinity. Alright, so these are the little stuff that you need to really practice. And therefore I can rearrange this one, because means we know that this is simply z transform of u. So therefore I can write, not forgetting that there is a z minus 1 constant over here, and then I have a u z. So in other words, what we have learned over here is that you can actually rewrite this z transform. Since it's ek, you can make it capital E z, something of this, some sort of this meaning. In other words, if you were to have a Laplace transform of y of t, you can rewrite as y of s, correct? So this is just the same meaning. So this is the notation if you feel that is uncomfortable or feel that what the hell am I talking. So they are just using the same form of Laplace to apply in Z transform. So these are something of a new language that you need to like so-called download into your brain. So therefore, let's download the rest of the stuff. Since we know that this chunk over here can be represented as this one, therefore I sub in as over here. Okay, then this one is in terms of EK, so I can write in capital capital EZ. Alright, it's just the same notation as capital capital where? Capital UZ. Alright, because it's in terms of U, so it's UZ. If it's in terms of E, then it's EZ. If it's in terms of Y, then it's YZ. Alright, these are the little stuff. And as for this case, this is very similar to your UK minus 1. Right? You apply the similar method of solving, you should get something like this also. Z minus 1 EZ. Okay? I think this is pretty much quite clear. This is where we last stopped. I just clean things up a little bit. Okay, so just the take note is that Z minus 1 is a time shift delay. And we call this the one time delay or one time shift delay because it's Z minus 1. If it's Z minus 2, then it's a 2 time shift delay. If it's Z minus 3, then it's 3 time shift delay, things like that. Why? It's because you're talking about K minus 1. K minus 1 is minus 1 shift delay. Right? It's one time step behind K. So if it's minus 2, then it's 2 time shift delay, which is what I'm talking all along. Okay? Now, what we're gonna do now is to change it into a transfer function. For a transfer function, I'll just bring, because UZ is over here, there is also a UZ over here. I'll just bring it to the other side. When I do that, I have UZ 1 minus Z minus 1 is equals to, because I'm just simply factorizing out the UZ now, alright? And then now it's T over 2. Instead of EZ, alright, over here I can factorize them out. Alright, instead of factorizing out at the front, I'm factorizing out at the back. So I have 1 plus Z minus 1 EZ. Alright, why I put it behind is because I just want to show you it's the same thing. Alright, and now I'll just bring this thing downwards. Alright, if I were to do that, meaning I'm gonna divide everything. Right, I just shift this thing over here, and there you go. This is your stuff, which is the same as this, and then you simply bring the EZ down. I think the rest you should know. This is the transfer function. We call this the HZ. Alright, as for trapezoid differential, alright, Z transform of trapezoid differential, and over this page he said that in the future we'll discuss about it. It's a testing method by linear transformation. I don't know what the hell, but yeah, this is it for the Z transform for a simple trapezoid integration. Just to know, get a feel of it. Just to know that last recap is that this one is the Z transform, and if it's in terms of E, then it's EZ. Alright, if it's in terms of U, then it's UZ. Alright, because it's transforming like this. I hope this is somewhat pretty clear, and I shall see you in the next video for other stuff.